Okay, step away from
What
the
a
board.
wonderful summer.
So yesterday I sent out that email about, someone made me, make the test harder, and maybe it was someone in the first row, maybe it was
harder. It was really hard.
It's funny. A couple of people just assumed it was Ahmed. And they emailed me, well, maybe Ahmed is a math major. Maybe Ahmed is really passionate. Maybe he doesn't know what he's talking about. You guys need to seriously stop picking on Ahmed, okay? Stop it.
It's just so much fun.
Stop picking on Ahmed. That's what I said. You guys are just mean.
Yes, we are, and we're bullies.
Right. Hopefully you've noticed the information here. So, like I said, test score is on July 17th. That we already know, but it only covers up to 8.4. Because I expect to finish 8.4 either on Monday or maybe by the first half of Tuesday's class. And then anything I teach after that, I don't think it's fair for me to put a test on that on Thursday. Yeah, so the homework for that is due on the day before the test so that we can talk about it and review some problems. And then the review for the finals on the 21st. If you're going to show up, you can hand in homeworks 8.5 and 8.7 on that day. If you're not showing up for the review, you have to hand it in the Thursday before that. Because then by the final, that's true.
Are you gonna take assignments for
Oh,
21?
No, that's not.
and what about the
official
Mat
class.
Lab? You said you were going to give us a take-home final for that?
Something like that, yeah. Don't worry. Okay, 8.1. If you're doing the first edition, I don't remember if I left this out of the syllabus or not. Skip problem 39. If you're in the second edition, don't skip 39, but also do 41. So. Yeah, that's it. So,
I got the first one already. I got both.
I sent you the PDF.
now we're going to continue with 8.1. Tell you some more facts about sequences that will come in handy even when we're doing series, which is 8.2 onwards. Where did I stop last time? Squeeze theorem, I think, and absolute value, blah, blah, blah. Okay, by the way, look at something like this. Well, let's say I said AN was given by this guy. How do you find that limit?
We find the limit of that.
Yes, the limit of that as n approaches infinity. By the way, everyone knows what this symbol means? Factorial, yeah. I wasn't like excited and exclaiming, oh, n! Yeah. It actually means something. It's n over n to the n. No. this actually means something. N factorial, where n is an integer, is the product of all integers from 1 up to n, right? So this is just, think of it as n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So, example, if I say 5 factorial, that's the same as saying 5 times 4 times 3 times 2 times 1, which is 1 term, right? That's what that means. So factorial just means I'm multiplying all integers from 1 up to the integer n. Okay, so what is that limit?
0.
It is 0. How do you know?
You
Because
can
both-
separate, you can get a range for the AN is smaller than 0 and bigger than 1. I mean, bigger than 1 over n.
Okay, so one way you can see this is n to the n just means n times itself n times, right? So if you're looking at the limit of n factorial over n to the n, you can sort of think of this as the limit of 1 times 2 times 3. Right? And this is all divided by n by itself. The same amount of times. Right? Now, obviously here, this n cancels. Here, you can take a 1 over n factor out, and what do we have over here? This is 2 times 3 times all the way up to n minus 2, n minus 1, and n. Right? Now, what do you notice about this number here?
Very small number.
What's its size? Can you give me an estimation?
Smaller than 1.
Some sort of amount. It's less than 1, right? Because all of the top numbers are smaller than each of the bottom numbers, right? For all of them. So this is actually less than 1. So this guy is actually less than the limit of 1 over n, right? This means that if you take the limit of an in absolute values, it's less than or equal to the limit 1 over n. This means that the limit of an is less than or equal to 0, but right? Because limit as n goes to infinity, this is 0, right? Which implies the limit of an is 0 by the squeeze theorem that I mentioned before. Now, what does that mean, right? If I take this divided by this, take the limit as n goes to infinity, I get 0. What does that tell you about the relationship between these two guys? Hmm? In terms of size, maybe, or growth rate. Huh? N to the n is larger. It grows faster and it gets much bigger, right? So as you're going to infinity, this guy gets so big, it's like this guy's not even trying. It's just like a constant over a huge number. That's where you get limit equals 0, right? If you have like a constant over infinity, that gives you 0. So this is saying this guy grows a lot faster than that guy when your n is getting huge, right? This will always be way bigger than the factorial, which is going to help us a lot, because a lot of times we're going to be doing comparisons between different kinds of formulas, and we're going to need to know who's the bigger one, who's the smaller one, because that will come in handy. So with this, so some of these you knew before Calc 3, but at least now you know, with this one, you know the final piece of the puzzle is that in general, logs polynomials, where this represents logs, this represents polynomials, right? The a is a constant. This represents exponential functions. This represents factorial functions. And this, I forgot what those are called, right? But those are the relationships. So logs grow a lot slower than polynomials, right? So if you ever have a limit where a log is on top and a polynomial is on the bottom, you know it goes to 0. Vice versa, you know it goes to infinity, right? Similarly here, polynomials grow a lot slower than exponentials. So as your n is going to infinity, this guy is going to be huge in respect to this guy. Factorials are a lot bigger than exponentials, right? So when you're going to infinity, this guy is huge compared to that guy, and so on and so forth, right? Knowing who's bigger can help you to talk about limits, especially when you have ratios, and that's going to be really important later, to know who's bigger than who. Okay? So that's actually a very, very important fact that will help you, especially with limits, but of course with other things. So for those of you who have learned about sequences before, odds are you started out by considering two basic types of sequence. One was the arithmetic sequence and another was the geometric sequence, right? The arithmetic sequence is, it's sort of going to be obvious how things like that work out, but I really want to emphasize the geometric sequence, because that's going to show up all the time. This is a sequence of the form AR to the n. I'll just make it non-zero for the time being. Non-zero constants. Because if there's zero, it's not very useful. Okay, one important fact. The geometric sequence converges if so there's only one situation in which your geometric sequence will converge to a constant number that's not infinity, and it's if your r is within this range. And if your r is strictly between -1 and 1, it will converge to 0. If your r is equal to 1 on the edge, then it converges to 1, which means that AR to the n will converge to A. That's an important fact. Say, this is the last important fact from 8.1 that we need. I'll flesh this out a little bit. Called monotonicity. Okay. What does monotone mean?
single volume.
Yeah.
Strictly increasing or strictly decreasing?
Yeah, it's just something that is always the same, right? In this case, in math, it refers to increasing or decreasing, your rate of change. This is basically just saying strictly increasing or strictly decreasing sequences is said to be monotone. Right? So if you have a sequence of terms where each number is always getting larger, greater than or equal to the previous one, or it's always getting less than or equal to the previous one, you say you have a monotone sequence. Okay, what else do we get? And just the last part of it, the n is said to be increasing if each new term is bigger than the previous one. Each term is less than the previous one, it's decreasing. So in that case, monotone means an plus 1 is always greater than or equal to an, or the exclusive or an plus 1 is less than or equal to an. So increasing means each new term is bigger than the previous one. Decreasing means each new term is smaller than the previous one. And if this is always true for all terms, or that is always true for all terms, you say it's monotone. In this case, it's monotone increasing. In this case, it's monotone decreasing. Okay.
And the strictly means you get rid of the equal.
Yeah, strictly just means you get rid of the equal.
Right.
Right. Let's see. Sometimes this is hard to prove because of the algebra. Our an can have really complicated formulas, so there's actually another way we can talk about increasing and decreasing. And what way do you think that is?
The boundary,
The what?
it says the boundary, if it's number prime,
Hmm?
f prime.
The derivative, right. Increasing, decreasing. By finding the derivative. Right? an increasing means your derivative of an, with respect to n of course, is greater than 0. Right? Or an decreasing means your derivative is less than 0. Okay? So calculus, we can use calculus here. There's no law against it. Sometimes just seeing it from the algebra is good enough, but sometimes this thing is really messy, and to prove that this term is actually bigger than that term is sort of difficult. So in that case, you can just find the derivative and see if it's greater than 0 or less than 0. So here's a question and a couple examples on this. Is 1 over n monotone? Monotone increasing or decreasing?
Decreasing,
How do we know?
because the bigger the range gets. the
Note that
smaller.
an plus 1 is just 1 over n plus 1, which if you make the denominator smaller, your fraction will get bigger. This means an plus 1 is each new term is smaller than the last one, right? Alternatively, you could see that an prime is actually equal to minus 1 over n squared. Now this, of course, is always positive for all integers, which means your derivative is always 0, less than 0. Because answer is positive for all non-negative integers.
So you just need to prove that it works with between the two different terms?
Yeah.
Okay.
Mhm. So this is one way to show decreasing, and in this case monotonically decreasing, right? So you either prove that the next term is bigger or smaller than the last term. In this case it was easy because the formula was easy. It's just a fraction. You can see clearly, oh, the denominator here is bigger than that one. It's not always that simple. In that case you can try the derivative, and that one might be more obvious. You'll be able to see, oh, it's always negative. Yeah.
Should that be a to the subscript n or n plus 1? You say monotonically decreasing.
What this
No, the one below. Should
this?
that be below? A to the n plus 1?
Yes,
Should that be a to the
this
n?
is all subscript. This is all subscript.
That shouldn't be n. Okay. So you say that
wait,
n plus...
an.
Yeah.
Alright, so that's just a very simple illustration of how you would determine this. You either look at each term and algebraically determine it somehow, or if you can't do it algebraically, you can use the derivative and try to determine it that way. Right? The sign of the derivative can also tell you if it's decreasing. And that's going to be important later. But that actually ends 8.1. Those are all the facts we need to know about sequences to move on to 8.2. Well, 8.2, 3, and 4, I'm sort of going to combine them. Because really what they do is they go through all the convergence tests which are on the handout that I gave you last class. So 8.2 covers the first 2 tests, 8.3 covers the next 4, and 8.4 covers the rest. So if we go through this one page, we'll kill all those 3 chapters. So I just thought it's a great way to organize it and just get through the problems that way. So we're going to do them all at once by just going through examples on the sheet. But I guess some words of introduction are in order.
Does this mean that all 3 chapters of homework is going to be due tomorrow?
No, I wrote down
do
two
one
here.
down.
Oh,
They're all
okay.
due Wednesday.
Wednesday, okay.
Yeah.
How about 8.1?
Personally, I don't think what we're going to be doing this series is hard, but it's sort of something you have to get used to. So I want you guys to mull over it for a while and just, because it's different enough from calculus. It's like you're switching gears. Like, what the hell just happened? Okay, it's just like we're going from triple integrals and now we're doing like, what's going on, right? So just, I'll give you guys some time to switch gears and get ready for the test. Okay, so when we're talking about series means sum, right? Like a Riemann sum. But we can think of it as the sum of the terms of a sequence. And the notation, which I'm sure you've seen before, is just this thing called sigma, right? So capital sigma. And it can tell you where you start adding things to where you want to end adding things. So if I say this guy, it really means I'm adding all the terms from n counting up, right? So this is a1 plus A2 plus A3 plus, right? Going on to it, right? Or on another example, I can say the sum equals 1 to 5 of an is just a1 plus a2 plus a3 plus a4 plus a5, right? So a series can be a finite sum or it can be an infinite sum. Finite sums are way too easy. Of course, we're going to be doing with infinite sums all the time. Okay. Because finite sum, you just add a finite number of terms. It's not really a big deal. And you sort of learned how to add, you know, like the first n integers and the first n squares and the first n cubes. You learned that when you were learning Riemann sums, so you don't need. So can use this when it's clear that n is the thing that I'm counting up by, or the sum of an, if understood. So it's just shorthand. Sometimes I'll get sloppy with how I write the series, but it should be obvious what the limits are. If not, I'll write them down. But just be aware of that. Let's see, what else do I want to mention? So just like sequences, some series converge and some diverge. Basically means they sum to a finite number. And yes, this includes infinite sums. It's possible to add an infinite number of things and you come up with a finite answer. Right? And it's sort of weird when you think about it, but it's actually true. Like non-zero things. You can have an infinite number of non-zero things, come up with a finite answer. It's sort of like back in Calc 2 when we were doing improper integrals, you're integrating on an infinite interval, and yet you come up with a finite answer, right? So the area was finite. So it's sort of the same kind of notion.
It's like denumerable versus non-denumerable.
That's not exactly the same context. Denumerable and non-denumerable is more in the context of sets. Right? Like if you have an infinite set, if you can count the elements, you say it's denumerable. If you can't, it's not denumerable. Yeah, so some series can converge, meaning they actually can become a finite number, right? So, what else do I want to say about that? And it's particularly important in the sense of when we get to Taylor polynomials, you'll see why we care if something converges. Because it will be the case that sometimes it's a lot easier to represent functions as series in order to do calculus and other things. And so you need to know if this series is actually a number you can play around with. If the series is infinity, then you can't really do math with it in a conventional sense. And so it's going to be important to know which is happening. Right? So when we get to Taylor polynomials, that's like 8.6, 8.5, 8.6, 8.7, around there. We'll get to see functions represented as series, and then we're going to want to know where these series work. So it's going to be important to know when our series actually give us a finite answer, a number that we can do math with. Right? And so knowing when they converge is going to be important, and which is what the handout I gave you about. It tells you a bunch of tests that you can take on series where if it has a certain form, you can know if it converges if this happens. Right? Strictly speaking, this is mathematically the definition. So to determine if a series converges, one way to do it is to see if the sequence, as in 8.1, of partial sums converge. And I'm going to show you an example of that right now. This is actually based on the fact of how we define a series, an infinite series. This is actually thought of as the limit as big N goes to infinity. Example. From 0. Well, I started with 1. Maybe I should maybe mention more what a partial sum is. Let Sn be the sequence of partial sums. Right? That is, S1 is equal to A1, which is a half, which is the sum of the first terms. S2 just means you add the first two terms. Right? This is just going to be a half plus a quarter, which is going to be 3/4. From the first two terms. Right? That's sort of what a partial sum means. A sum of the first, some finite set of the terms starting from the beginning. Okay? So S3, what would S3 be? 1/2 plus 1/4 plus 1/8. Right? Which is, what's that?
4 plus 2 plus 1.
7/8, which is the sum of the first 3 terms. Right? So if you use a sequence to measure the sum of the first n terms, right? S1 is the sum of the first term, S2 is the sum of the first 2 terms, 3 is the sum of the first 3 terms, S4 is the sum of the first 4 terms, S5 is the sum of the first 5 terms, etc., etc. Then, if that sequence converges, right? This gives sequence Sn is just 1/2, 3/4, 7/8, and so on and so forth, right? So I'm using a sequence to measure the sum of the first n terms. This is called the partial sum, right? And I'm giving a sequence of partial sums. It turns out that if this sequence converges, then my original sum converges, and in fact it converges to the same number as this guy converges to. So could you figure out what this converges to?
2, 1.
How did you get that?
Because, oh, not 1, I'm sorry, like 2 no, I'm not sure.
No, well, remember, when we had the sequence, a list of numbers, how do we
Because
try
it's
to
getting better,
determine it?
bigger. It's,
It's 1.
it is one.
It's one because
You
you
can
keep
Yeah.
on
divide it
dividing the
differently.
amount that you add to it. So it's like you never add any more. than-
Yeah, so why would it go to 1? Why wouldn't it go to 0.9?
It never reaches 1, but it may
Well, if you
reach
go-
9,
Keep on going.
999.
The limit
Yeah.
is
So
one.
here's an idea. What you can do is pretend like you have a square sheet of paper.
Okay.
Like, I'm sorry, not length 1, but if you fold it in half and you kept folding it in half,
Mhm.
it's similar to like this sequence,
Okay.
right? But it still holds the same area. Like if you have 1
Okay.
divided into 2, that's 1/2. Right?
Give me a mathematical argument. I gave you this list of numbers. How would you figure out if it converges to something or not? How do you know if a sequence converges?
Take the limit.
You have to take the limit. How do you know how to take the limit of that?
Express it as a function.
Express it as a formula. Express that as a formula.
I have a calc for that part.
Well, it's like-
I actually did that in 8.1. I did an example of this. Yeah?
2 to the n minus 1 over 2 to the n.
Right, here, Sn is actually 2 to the n minus 1 over 2 to the n. And the limit, as n goes to infinity, of this guy is what?
One.
It's 1.
1.
Right? So, the series, this guy, converges, and it converges to 1. In this case, I mean exclamation. Well, 1 factorial is also 1 anyway, so either way you want to interpret it is fine. Right? So if you can take the sequence of partial sums when you're adding up terms as you go out to infinity, and that guy converges, then your series will converge to the same number.
I have a question. If the limit of a series, if you just take the series and you take away that b thingy, you get the limit, and that approaches a number, does that mean the series converges?
No.
So I got that to try it on.
But there's a very similar, if you look at the sheet that I gave you, there's something called the kth term test, which you might also see referred to as a test for divergence. right? You can actually use that notion to tell for sure that it does not converge, right? So if you actually do that limit and you get something that's not 0, you know for certain that it does not converge, right? Finding out that it does converge is a little bit harder than that. Could be a lot harder than that. Let's see, what else do I say? I'm talking about this guy. We're actually going to talk about that in far more detail. But yeah, knowing when a series converges is pretty important. Converges mean the sequence of partial sums converge, which means if you use a sequence to measure adding a certain number of the first number of terms, if that guy converges, then your series actually converges, and it converges to that number specifically. Okay? Again, that's not always very easy to do. A lot of the times you'll just know that something converges, but we won't be able to tell to what. And that's normal. But sometimes just knowing that it converges in general is good enough for our purposes. Yeah, because finding this guy, finding that SN in general, it's actually pretty tough. Not always, the numbers aren't always so nice. Okay. So that actually leads us to this guy. I actually want to mention something else. I actually want to mention something else before. This is called a telescoping series. So let me talk about what that is. I don't know why it's called telescoping, I can't really tell you. But it's a series where most terms cancel themselves out. So you only have to add so you have to add a manageable number of terms. Example, FYI. Hopefully you remember partial fractions. We haven't done much of it, but it's coming back. Example. The series 1 over n times n plus 1, as n goes from, I thought I made it 1 to infinity, is a telescoping sum. Let's actually find if it converges, and if so, to what does it converge? Note. This guy is actually equal to the limit as n goes to infinity. Remember, of this guy. That is equal to the limit as n goes to infinity of. Now the idea is, I'm actually going to find the partial fractions of these. Alright, so remember how to find partial fractions, right? You factor the denominator, that's going to be all your denominators. So we know there's going to be something with an n and something with an n plus 1. And then we want to figure out what are the constants up here, and there are many ways to do it. You can do combine the fractions and taking like terms. Tons of ways you can do this. Anyway, the easiest way for guys like this would be to figure out what makes this 0, cover that up, and plug it in, right? So to make the denominator of this 0, n would have to be 0, cover up here, and plug in n equals 0, you get 1. To make this 0, n would have to be minus 1, cover that up here, plug in n equals minus 1, so this is actually minus 1. Get to that however you want to get to it, just get to it quickly.
You're basically doing partial decomposition.
Partial fraction decomposition, yeah, that's what I meant. Right? So you see that, you do a partial fraction decomposition, right? And now what that means, start to look at what the terms here look like now, right? Now the first term is what? Well, plug in n equals 1, so this is just 1 minus a half, right? That's when n equals 1. Plus, the second term is a half minus a third, right? That's when n equals 2. Third term is a third minus a fourth, plus so on, right? If you're down to the, say, n equals n minus 2 term, this is actually 1 over n minus 2 minus 1 over n minus 1 plus 1 over n minus 1 minus 1 over n. This is the n equals n minus 1 term. Plus the last term in the finite sequence, the partial sum would be 1 over n minus 1 over n plus 1. Okay. Now when I write the partial fractions decomp and I try to write out the partial sums, what do I notice? Well, the halves are going to cancel themselves, right? The thirds cancel themselves. The fourth is going to cancel itself with the first term in the n fourth power. This is going to continue, right? I'm just writing out enough terms so I can see a pattern of what's canceling, right? Notice that here, this cancels that, this will cancel that. This guy is going to be canceled by the last term in the previous one, so that's going to cancel. So basically at the end of the day, everything cancels except those two terms. So I'm only left with, at the end of the day, 1 minus 1 over n plus 1. Now as I take the limit of, as n goes to infinity of that, I get 1, right? Well, all that means is that the sum 1 to infinity of 1 over n plus 1 is also 1. And this is a very special kind of series. This will happen often if you're given something where you can do a partial fraction decomposition, and you notice that all the middle terms will cancel out. Or a lot of the terms will cancel out, and then you sort of just take the limit after that. Right? So So that's another very important kind of sum that you will see often enough. Okay, and we'll stop there. So next time we'll go through these guys and we'll see far more efficient ways than these of finding the sums.